Miles, well, thank you very much for sort of agreeing to talk with us. It's a really nice opportunity to sort of get to know each other with our common interests. So please take it away.
Thanks, Bill. Yeah, William, sorry. Nice to hear that. It was nice to hear that you're working along similar lines and you have a project. So I hope some of this is helpful for the way you're thinking about things. At least perhaps branching out. And part of the mission here is to branch out our understanding of what interdisciplinarity could be. I think there's kind of a rather narrow conceptualization of what it is in the science policy domain, which forces people into certain ways of doing interdisciplinarity, which is not the only way in which interdisciplinarity could happen, and may not even be the ideal in many circumstances. So that's where I'm coming from actually with this talk, and that's where I'm going. I'm trying to bring philosophy of science to bear to that, to make some of these arguments. So I'm borrowing from a few people's domains, few people's theories to make that argument. I think the basic underlying criticism is that this mainstream model has been formulated without necessarily having good kind of underlying models of scientific practice. So I'm trying to bring those models of scientific practice to bear. Okay, let me share my screen then. Now I've got to find where that is. Share, not share, what share screen? Okay. Okay, share. Everyone's got that? Just turn it on. Good. Next. Okay. Okay, I won't say too much about this. We can come back to it if you like. I don't know if you've seen this diagram, but it's very interesting kind of model of the interdisciplinary landscape that's out there. And you can learn a lot about who works with whom by looking at this kind of diagram here. It's a diagram of citation, co-citation patterns. So that's what it's tracking there, which is often how scientometrics works when trying to get a pin on how much interdisciplinarity is going on or who's talking to who across the various fields. And you can kind of see where people position themselves and who doesn't talk much with who. So, you might notice that engineering and social science are kind of on the opposite sides of this kind of domain. You have to go through a lot of nodes to get to each other, which when you think about the kinds of imperatives that people have with respect to interdisciplinarity, seem problematic, right? Because we want engineers to be working with people in areas of social science or social studies. So that's the kind of thing people notice from these diagrams, and they wonder, well, how do we go about solving these kinds of problems? And we'll come back to that. Just a bit about my background. So I've been looking at interdisciplinarity for 10 years now, I think, doing various empirical projects, so ethnographic projects, interview studies. Two areas I've looked at, systems biology and environmental science. I'm drawing some generalizations here based on stuff that happens in other areas of the literature as well, but that's principally the origin of my thoughts, what's going on in those two fields. So maybe you could bear what I say a little bit of grain of salt on that basis. And I'm happy to hear other people's experiences. I also do a lot of work now collaborating with education scientists. I'm trying to apply some of this stuff in the educational domain. The University of Fender, it's a technical university, so all the students have to do interdisciplinary problem solving. So they get thrown in groups together with people from other domains at least once or twice during their bachelor thesis, and are asked to work on an interdisciplinary problem. That, of course, works to different degrees of success. There are all kinds of difficulties. I'm happy to discuss that too, if people would like to discuss that. University of Twente, by the way, if you don't know, it's about 13,000 students. It's if you go to Amsterdam and you just go straight across to the German border, you'll find us. We're right on the German border there. One of 3, or is it 4? 3.5 technical universities in the Netherlands. There's also an agricultural university in the Netherlands. Okay. All right. So here's some just basic entry-level stuff. So there's nothing particularly new about interdisciplinarity. Sorry, that's okay. Go back. But it's certainly a principal policy objective of funders at international, national, and university levels. Across scientific domains in different countries, We can talk, for instance, about funding instruments that are specifically geared towards interdisciplinarity, or at least that interdisciplinarity is often an objective on funding instruments, something that's considered a epistemological good, if you can bring that into a project. Now, there is, what I'm going to say here is there's kind of a mainstream view on interdisciplinarity, which motivates and justifies the kind of funding strategies and the way funding instruments look. And I'm going to consider this view in light of various theoretical perspectives from philosophy of science. Here's what I think is the mainstream view, or how interdisciplinarity is conceptualized in the mainstream view. And it's this view, as I said, that informs funding policy. And then there's kind of a tight coupling between these three things: real world problem solving, integration in the sense of methodological innovation, or at least leading to methodological innovation, and collaboration, the heart of things. We do interdisciplinarity because we're trying to solve real world problems, and these real world problems cross disciplinary boundaries. So in some sense, interdisciplinarity is just necessary. We can't solve these problems otherwise, so we need to engage with real world problem solving. There's also a bit of a feedback loop, because if we expect innovation to come out of interdisciplinarity, it's really the constraints of real world problems which can drive that innovation, right? Because if you're confronted with real world problems, which cross disciplinary boundaries, then you can't optimally solve these things unless you relax your disciplinary constraints in some ways and try to work outside those boundaries. At the same time, given that existing methodologies are not sufficient in themselves to solve these kinds of problems, we need to methodologically innovate, and integration is seen as the kind of pathway through it. That methodological innovation will happen. Words like transformation and synthesis, there's a lot of kind of metaphors in this domain are used to describe what we mean. Blending, the metaphor you see. Basic idea is somehow methods come together, or methodological approaches come together, and through this kind of back and forth process, we get something new that comes out of this dynamic, which isn't reducible to what we started with. And lastly, collaboration. So the thought behind collaboration here, one of the thoughts behind collaboration is that if you put people together from different disciplinary backgrounds, then they're kind of forced to confront their disciplinary perspectives, forced to negotiate with respect to their disciplinary perspectives, and then through the process again, forced to move outside those domains. So that you can see this kind of coupling to this view. And if you look at funding instruments, you'll often find, with respect to interdisciplinarity, you will often find all three listed there in the funding document as the things that we want to tick in order to give you funding. So I'm going to suggest here that this is quite a narrow conceptualization of what interdisciplinarity can be about, or what we should aim for with respect to interdisciplinarity. With respect to all three, really. So interdisciplinary work can be non-integrative or multidisciplinary. About that. Often multidisciplinarity has a kind of negative sense. It's what you end up with if you failed in your interdisciplinary project. There are good reasons not to look at things like that. Interdisciplinary work can be non-collaborative. I'll say a bit about that at the end. In fact, I'll have quite a bit to say at the end about this. Suffice to say that in the history of science, there's lots of examples of quite innovative interdisciplinary work, which is not collaborative in the sense that people haven't worked across interdisciplinary boundaries together to get there. And interdisciplinary work can be theoretical rather than simply devoted to solving real world problems right there in the space of that funding instrument. And what I mean by that is you can work on theoretical problems of combining disciplines together, which might not have any meaningful practical outcome in the first instance or right there, but can be quite valuable work to do. And none of this kind of stuff necessarily fits within the way interdisciplinarity is conceptualized at the policy level. And so I guess the normative case here, or the normative story at the end is, can we go beyond this? Okay. Now, if we talk about kind of this, given the way interdisciplinarity is set up, what's going on out there? It can be quite hard to get a kind of clearer view of how well the situation is working. I think the empirical information gives kind of a mixed story about what's going on. So let me run through that a bit. There's a lot of stuff. There's a lot of stuff out there. A lot of it comes from scientometrics, but also from other areas like science technology studies. Also, some research of my own, studying interdisciplinary interactions. You get different results. This is a bit of kind of. I'm at risk of cherry picking here, just so you know. But I would say that cherry picking is somewhat a result of the fact that stuff is a little bit all over the place. First thing to note, which isn't really an empirical point, but it's worth noting that in many cases, interdisciplinarity is carried on without any fuss, really. So long tradition of engineers working with one another, right? Or working with some natural scientists, at least, long tradition of mathematicians working, and now computer scientists, of course, are working extensively with various people. So in that sense, when people say interdisciplinarity is a problem or it's difficult, it's not with everybody that we're talking about. That's worth bearing in mind. Studies tend to be quite mixed on whether interdisciplinary research produces more citations or impact, so whether it's more impact related research. You get studies going either way, but it does appear that if you want to see citation, if you study the progress of citations, it takes longer for interdisciplinary research to have an impact. The top 1% most cited papers exhibit high levels of interdisciplinarity than other papers in other citation classes, and that this relationship is observed in more than 90% of NSF specialities, which might kind of behind this motivation that, you know, collaborative interdisciplinarity can really kind of promote innovation. When you see stuff like that, we're talking about kind of elite papers though. Variety has a positive effect on impact in some studies. When variation is high, so it correlates with, you know, there's a large number of fields involved. But balance and disparity can have a negative impact, which is interesting, right? But it's the interest of disparity. So if the disciplines are sensed as being not particularly close to one another, or not particularly likely to have something, or are kind of too distant from each other, then that can have a negative effect. And balance refers to, well, how well distributed is the balance between the disciplines involved. Is the work clearly led by one domain, or is it not? And more balance can somewhat negatively affect evaluation. But there has been a study that's kind of contradicted that recently. So yeah, here and there. Interdisciplinary papers are retracted more often. That's kind of recent research. And there is this view out there, of course, not shared by all researchers, but it's documented among, say, researchers who are engaged in interdisciplinary work, that their research is often less reliable or interesting when compared to research they do within their domains. Many qualitative studies from all over the place reveal that collaborative projects often fail to produce this kind of genuinely interdisciplinary or integrative style result. So this kind of novel methodological synthesis or innovation seems rare within these kinds of funding domains, within this kind of traditional way in which we're setting up interdisciplinary research. And if you would look closely at it, most interdisciplinary research does appear to be multidisciplinary in character rather than interdisciplinary. What does that mean? It means that researchers divide the tasks up into domain-specific tasks. So they take a problem, they divide it up into domain-specific tasks, and they go away and they do that, and they come back at the end and they put that together. But there's not a lot of evidence that it's common that you'll have this kind of consistent engagement, which is kind of hoped for from these kinds of within interdisciplinarity, within the, you know, within the attitudes of those who argue for interdisciplinarity. In my experience, much interdisciplinarity involves a kind of input or transfer relation, kind of contribution of information kind of relation, where people figure out that they can get something maybe useful for their own methodologies that another domain can provide, some kind of data, for instance, and then they'll take that data and they'll, you know, feed it into their own ways of working, and so they'll get leverage. They'll get some kind of leverage out of the situation, but it doesn't necessarily involve anybody seriously rethinking their methodological approaches. deep kind of way. Okay. So I just give you one example of, which is nice, which I can talk about, which kind of reiterates some of those points. So it's one study I've done with some colleagues, 4 years of a Scandinavian technological university, which basically implemented exactly this kind of funding policy where the researchers had to tick those boxes, but they also had to exhibit strong links to the corporate community as well, kind of an additional hurdle to jump through. How did this work? Well, in 2015, the researchers were told they were no longer getting their internal funding, which was allocated more traditional basis, such that everybody would get some internal funding. They were told, now you only get internal funding if you set up a platform which is interdisciplinary, in which somebody from every school, there were 3 schools, business, engineering, and science, were involved. And it had to be on a real world problem, right? And it had to be engaged in kind of methodological innovation. So everybody was told that. You can imagine how that went down at the start, right? That was, I mean, the main complaint, which is interesting. So it wasn't that they'd been forced to being interdisciplinary, although, of course, that was a problem for some. It was that they were forced to spend time competing for their own funds, even though they spent enormous amounts of time competing for European funds or whatever. Now they were told they had to compete for their own funds, and they didn't think that was particularly good use of that. So when you look closely at what's come out of these platforms, so there were 5-year platforms, what you do see is kind of what I just said before. You do get interaction between some. So for some platforms, there was a genuine kind of attempt to think through problems, to find maybe new ways, but it's invariably ended in with this kind of exchange kind of relationship. So in one instance, for instance, engineers working with business scientists, engineers designing construction equipment decided, well, often we do these kinds of customer evaluations to try and improve our designs. We've got business scientists involved. Let's just get the business scientists to do that. And there was a little bit of, well, we're kind of business scientists, we have our own theoretical agenda. Not really a service. We're not really a service kind of thing. But in the end, they found a kind of way to make that productive for them. But it does end up being this kind of thing, right? The engineers just carry on, but they kind of get a better sense of what the customers want, which they can use in their design process. So there is a kind of leverage there. But in terms of, again, methodological innovation, methodological advancement, it's quite limited. A lot of those platforms didn't end up even with something like that. They more just kind of became collectives for allocating resources around a kind of problem. And so nobody's really trying to coordinate their methods. Rather, they're trying to kind of coordinate their labor for dealing with certain problems in different kinds of ways. Okay. So what's this talk about? Then to just be more precise. So I want to explain why this approach to ID, this kind of model of ID, might not be so effective, and why researchers make the choices they do when it comes to idea collaboration. I'll argue that institutional constraints, which is often the way these kinds of deviations from what we expect are explained, are not necessarily themselves sufficient to explain why scientists researchers make these choices. And I suggest we should consider or put support behind other forms of interdisciplinary engagement than those just suggested by this mainstream view. Okay, so what do researchers do? Well, I've kind of mentioned it, but I think it's a way to kind of summarize it to say that ID research is often quite conservative, to the extent that researchers do not engage in methodological transformation, innovation, or even often much exploration of what might be possible. Much ID research looks more multidisciplinary. So researchers find ways to kind of coordinate disciplinary methods and exchange information. And perhaps most interesting is that ID practices have a tendency in some fields, at least, to get kind of standardized. So rather than these kinds of spaces being kind of fluid spaces for open exploration of specific techniques for solving these specific problems, what we see is a tendency to what I call kind of crystallize practices around just specific sets of ways of interacting, and then develop those. So a tendency of interdisciplinary modeling practices in the environmental sciences, which is what I'm referring to specifically here, although I've seen something like it in systems biology as well, to coalesce around in a finite number of modeling strategies around which to structure their interactions, which goes against this kind of expectation. So I and a colleague, as well as some people within the fields of environmental science, have tried to look at the kinds of strategies that modelers use when interacting together. And it's quite a finite set of overarching strategies that they use to work together. So the kind of basic one, the entry-level one, which has certain advantages, is a kind of data-driven approach. It could just be something as simpler as a kind of linear regression analysis, which has great flexibility because everybody in the project can turn up with their variables, with their data, and throw them into a linear regression, as long as you can handle problems related to scale or whatever. Then you get a model, right? You get something out of that relationship. It's quite accessible and it's quite low level fruit. You can have something like an integral modeling approach, which might be something, especially in environmental science, like systems dynamics, which is often seen as a kind of a platform for doing interdisciplinary work, where again, people turn up with their variables and their causal relationships, and then they can relate different domains to each other causally. And then you have a model, as long as you can, of course, provide information on how the variables interact, what the mathematical relationship between those variables should be, then you have a model which you can kind of crank and get a cross-disciplinary representation. Most common, I think, at the moment is modular model coupling, where the different disciplines bring legacy models together, and then they get them to talk to one another. You're trying to solve a problem which works across some kind of boundary, it can be natural or social boundary. Look, we have existing models. One model covers this, one model covers that. Let's just get them to talk to each other dynamically and see what result we can get out of that. Let me just go to example now before I talk about the next one, just to give an example. So this is it's quite a large enterprise. The aim of this modeling structure was to predict the effect of climate change on snow tourism. So what's going to happen to the skiing industry? It's very topical right now in Europe, given we've had very little snow in the Alps. So how would you do that? Well, you take a climate model, right, which is predicting overall climate changes, and you get it to talk to a snow precipitation model, which will then help you predict snowfalls as a result of changes in kind of basic climate variables. They're built by different people, quite different specialists involved in those kinds of two models. Then you couple it with kind of an economic model, which predicts what will happen within economies, regional economies in particular, as a result of these things. And then you plug that into a kind of economic model, which is based around kind of tourism, so customer behavior with respect to, how much snow cover is there, how good is the snow, stuff like that. And then you crank those things together and you get a kind of dynamic prediction of what's going to happen. That's pretty common in the environmental sciences as a way to handle interdisciplinary relations and a way to get a kind of leverage over interdisciplinary problems. You can also have this more advanced option, which I like a lot, because to me, it's if I'm trying to think about integration and to give it a kind of concrete sense of what integration could mean, this to me is something like a gold standard, right? So there are certain levels in which models in which the kind of scale, which economics works and ecology works, come into nice alignment. And in fact, the modeling has a very similar kind of isomorphic structure. And you can do a lot with that, right? So here, if we talk about traditionally economic models of resource, say fisheries, is built on a basic structure where you have a kind of objective function, which say tracks the present value of whatever industry you're tracking or the particular business you're tracking. It feeds that information, it takes information on the natural resource, which is usually in some kind of biomass model, which is quite simplistic from an ecological perspective, a quite simplistic model, which feeds information about the resource and how the resource, growth rates, this kind of thing, into your objective function. And then you can run different strategies, run different management strategies, and decide what the optimum kind of strategy is for harvesting that resource, when to harvest it. For instance, if you look at ecology, they have something similar. They have a much more advanced kind of ecological theory, because they're ecologists, right? A much less advanced kind of objective function might just be based on maximum sustainable yield, for instance, traditionally. But because they've got this very similar structure, you get instant kind of very strong leverage by just substituting in the parts that you happen to be good at and taking out the parts you happen not to be good at. And you get a very robust kind of leverage in that situation. And so this happens. This has been done. And in some sense, it's become a kind of platform around which a lot of research, a lot of interdisciplinary research is done in the area of resource management. Okay, so we see this kind of crystallization effect. These various kind of, I'll use the word template. I'll use that later on because I think Humphrey's notion of templates has a kind of relevance here. Have various affordances and constraints with respect to interdisciplinarity. But here I just want to point out the phenomena, more or less, that there is this kind of tendency in the environmental science, at least, to kind of settle on the various platforms that we're going to use or rely upon to do interdisciplinarity. Okay. So you could talk about two views for why interdisciplinarity is not succeeding as hoped, is not generating this kind of methodological transformation, fundamental movement in the way we do science. And one is the kind of institutional view. And this is the idea that science and engineering practice is mostly, when it comes to these things, is mostly constrained by institutional factors. So we're talking about peer review. We're talking about what criteria you get promoted on. We're talking about, how grants get funded, who decides how grants, who assesses grants and how grants get funded, and so on. And so if scientists kind of step back from fully engaging in an interdisciplinary process, fully exploring the domain of interdisciplinary possibilities, it's because, some degree they don't see a payoff. They don't see that will be in their career interest to do something like that. And undoubtedly, there's a degree to which that's true. Scientists, researchers respond to institutional factors, and they do make judgments. There's a deeper argument that goes with this, that what might look like a cognitive constraint, and I'll talk about that in a second, is often really just an attitudinal problem by researchers. So it's just really a lack of openness and flexibility on behalf of researchers if they kind of stick to their domains in some sense and reassert their domains in this context. Is because of a lack of openness and flexibility. It's not because it's necessarily cognitive challenging, or that cognitive challenges couldn't be overcome with just some hard work and some ambition. And the difficulties of interaction, if there are difficulties of interaction, can often be boiled down to communication problems. Often you see language in interdisciplinary studies kind of areas of kind of putting kind of cognitive challenges and packing them into this idea of, well, communication. That, okay, we're just not right on the same page, but if we could get a better handle on communication, if we sit down and talk better management of our interactions through, say, group structures, then we could get past these things. What I want to assert here is I think that underplays the cognitive challenges that researchers often have in interdisciplinary contexts. And even though these institutional factors are at work, they're often entangled with cognitive practices, right? And cognitive issues. And these cognitive issues bite. So yeah, a scientist might not see it in their interest to engage in a difficult problem, but it's because it's difficult, right? To engage with. It would take a lot of effort, and they don't see that they don't see to some extent the payoff will be rewarded. Sometimes it's just, given the funding structure, it would just be very difficult to solve within a 4-year, 5-year, 6-year domain. So I'm going to give the cognitive view that the reasons researchers make choices they do is in some important degree at least cognitive. And achieving integration, methodological transformation, innovation is cognitively difficult, and cognitive distance between fields really does matter. So I mean, we're talking about engineers who are close together, so mechanical and electrical engineers, then cognitive distance is not that great. They share an underlying scientific basis with physics. It's not, there are some issues, of course, but for the most part, interaction can be relatively seamless, straightforward. But if you're talking, taking extreme, if you're talking about getting sociologists to work with civil engineers, then you may have quite a difference, quite a distance. And it can be a cognitive problem in the sense that it's very hard to cognitively integrate methodologies from both fields together. Okay, let's give some sense to that. Some ways of then accounting for the conservatism. So I'm going to engage with some philosophical theories here to try and understand, try and give some kind of flesh to this idea that cognitive constraints really matter. So this is the first one. So I borrow here from the systems of practice idea from Chang, kind of modified it a bit. And this is the idea that the scientific domain is a coherent system of interconnected values, assumptions, evidential standards, theories, modeling templates, experimental setups, and so on, plus, of course, institutional structures. But these are adapted to generate functional results for a given class of problems or research questions. And they've been adapted usually over many years, right, to be good at solving these problems in the ways that the researchers value. As a system, it can have properties of entrenchment, that various aspects can be upstream, various aspects can be downstream of one another. So modifying any of these can have implications downstream on the functionality of the problem-solving system and the ability, importantly, to kind of validate a result, to recognize when a result is reliable. This is important, right? It does mean that if you play with these systems too much, you can lose that functionality. If you modify these systems in various ways at various levels, you lose that functionality. And it also, which of course means that pushing these things too far, problematic. It also means you might have a basic kind of opacity problem, that it could be hard to recognize what the consequences are of messing with various aspects of the system. And you can understand in these situations that scientists might be very wary of intervening on various aspects of this problem-solving systems, or might find it difficult to understand where and how they could modify the systems to kind of align themselves better with somebody else's way of operating system of practice. And here's a couple of ways in which you might see that, well, there's kind of very deep disjunctions between these systems. So one, for instance, you might point to is in economics and ecology, two fields which are often hoped will work together much better ways. And of course, in certain domains, this is happening. So I mentioned resource harvesting, but that's an area in which the models do come into kind of scale alignment, but often there's a kind of scale misalignment between ecology and economics. What does that mean? Well, ecologists tend to work at a kind of local spatial scale and a long temporal scale. So the speed at which effects on ecological communities can happen operates over a long spatial temporal scale, which is different from economic systems, which operate in a short scale, recover fast, for instance, from impacts compared to ecological systems. And economics often operates at a regional spatial scale. Now, if you're bringing these two fields together, then you've got an issue here, of course, which is, well, how do we deal with this spatial gap, these scale gaps? And scale gaps are not easy to solve, right? We have, of course, industry involved in dealing with multi-scale modeling. It's very challenging, it's very difficult. Building multi-scale models often involves building in kind of uncertainties. You have to make averaging kinds of assumptions to get that kind of work. So it's not considered ideal, or at least it's challenging work to get it to work well. And you have other types of choices, of course. You could, well, let's just tell ecology to scale up and make much more regional models. But of course, given the complexity at which, at the kind of local spatial scale, you may be you're certainly asking an ecologist to do something outside their domain, but you might also be asking ecologists to build a model which they just consider too complex unless they make lots of assumptions which worry about, or they don't know how to how to handle very well. And the same thing with asking economics to kind of, well, why don't you just scale down to much more local levels? And maybe there exist models, frameworks to do that. Maybe you're asking economists to, again, make assumptions about how they might be able to kind of simplify environments so that they can just concentrate on the regional scale. Neither of these things are within the current competence, right, of how these work. The data collection skills, practices, etc., the aspects of the systems of practice which they're used to. So the argument here is that you're asking quite a lot cognitively of these researchers to do if you're asking them to somehow integrate their activities at cognitive level. You can also say the same thing with respect to different epistemic cognitive values, so different standards of evidence, different standards of practice. One thing that's been noted by Armsworth et al., I'm very interested in this actually, is a clash with how empirical modeling is looked at between ecology and economics. So you've got a highly theoretically orientated perspective in economics, which means when economics uses statistical regression, it's often to test a theoretical model. You start from a theoretical model and the statistical regression is there to test that model. Ecologists, however, are happy to build theory from empirical models, from statistical regression, and we'll use a principle like parsimonious to kind of select models kind of in order to understand causal structure. And parsimonious doesn't make much sense from the economic point of view, where you already have an underlying theory on how you might decide what's relevant in a given situation. And that's quite a distinct kind of clash there, right, on how you might use physical modeling, or concepts of explanation amongst biologists and modelers in computational biology, which has been noted by Fagan. I think that's quite interesting too. So if you look at some modelers in computational biology, you'll find that they have something that looks like a nominalogical account of explanation. It's really based on, well, there's kind of fundamental mathematical principles about systems that we can derive. So it might be based on, say, the landscape structure for, in the case of, say, stem cell potentialization, right? We're trying to understand how stem cells move into their different cell categories. We have a landscape model, which tells us how that does, and that's based on a very simplified understanding of systems, but we think we're getting at the underlying principles, those systems. That can be quite meaningless to molecular biologists. From the molecular biologist point of view, that's not really an explanation, because they actually want to know what's the mechanism by which this cell potentialization happens. And if I can't see which pieces are interacting with which pieces, then I don't really understand, in my view, how cell potentialization is stem cell division, stem cell potentialization is happening. Right. And then you've got a kind of significant clash, and you can understand it as a cognitive problem. Well, how can we recognize, kind of a philosophical cognitive problem, if you like, how do we reconcile this kind of different ways of understanding things, and how, as a result, how can we come to some kind of integrated way forward? And of course, you can imagine that, you know, within the context of a funding grant, you're not really going to be, you're going to balk at the idea of trying to solve those kinds of problems right out. Okay, just to give you one example, which I like a lot. So this is not my study, but we did talk to the people involved in the study and to the scientists involved too, because we thought it was quite interesting. It's a Baltic salmon fishery case from Finland, which the idea was to bring together fishery scientists, so something close to ecologists, sociologists in this case, and economists to work on the problem of salmon management in the Baltic, right? So a classic kind of overfishing problem. How do we manage this issue? How can we come up with a better management strategy to ensure that we kind of maximize the benefit for the industry? Well, not just the industry, in this case, society at large as well. The framework that was set up by the fisheries scientists was to use a Bayesian belief network system. So I guess in basic terms, a causal network structure, probabilistic causal network structure. So the various variables are interacting with other variables in which your input in this case is kind of management objectives and management decisions. And then you kind of follow the consequences of those down. And then you look at different scenarios and you try to figure out which might be the optimum management strategy to run. And the good thing about this, it fits within that kind of data-driven interdisciplinary approach to some degrees, or I guess also could fit within the integral kind of approach, because Bayesian belief networks are quite popular for this kind of work, is that you can bring in different kinds of people you wouldn't normally bring in. So sociologists could participate in this kind of collective. They just had to bring their variables, bring some kind of basic give some kind of basic judgment on what the prior probabilities might be, which even if they're not quantitative people, they might still be in a position to do, and I don't think they were in this case. So if you can see the diagram very well, but they particularly contributed to the kind of management objectives and the commitment, the notion of commitment here. So how committed are managers to various kinds of policies, and then probabilistically, how will that affect overall what outcomes we see given their degree of commitment. It was the economists that really had a hard time getting involved in this. Now, I'm not sure where the backstory is. I'm not sure why the economists got involved in this originally. We should have actually encountered this, because the project was built around a Bayesian belief network, but it seemed that very early on, once the economists became kind of familiar with that, they kind of refused to participate. And they refused to participate until they'd actually gone away and published some classical economic papers based on the data. And so at the very end of the project, they came back and said, okay, well, the stakes aren't so high for us anymore, so we will contribute. But what it came down to is that from an economic perspective, this just didn't look particularly meaningful to them. It was not something they could fit within the way they thought about how you would solve these kinds of problems. There's, for a few reasons. First, there are notions of utility there, which didn't make sense from the economic point of view, the notion of biological utility, right? There are ways economists might handle this. Some notions of willingness to pay, for instance, but that's not what was, being able to fit everything within an economic optimization framework. That's not how this was done. So they just processed different notions of utility and then kind of compared them visually. So the economists looked at this and said, "Ooh, this just doesn't look like anything that I'm familiar with, or anything I could kind of count as a meaningful way to approach this kind of problem." And so they checked out. There's a couple of quotes here, which I think you might find interesting. So from the fisheries biologist, right at the beginning, it became clear the economists did not have any motivation to play the common game, and I realized it was no use to try. So we had to knuckle under the fact that they have another perception of good science, which I think reinforces this kind of domain-specific aspect of how disciplines might interact. And then from the economist, it's easy to underestimate another discipline, to wonder what is the difficulty there if you only see some really reduced and simplified part of it and you don't understand the methods. You cannot know what amount of work there is behind that work. And if you don't know the literature of that discipline, you cannot understand what is the contribution of that study compared to previous results, which I like because I think it points out some of the systemic aspects of what I mentioned before. There's this whole system here of how we operate. It has a kind of rationalization. You don't see that from where your standpoint is, but that's very important. And so if we kind of see that with one another, then we can't really interact. Okay, so that's the first thing, which is to use this notion, the systemic notion of fields, to try and give some flesh to the idea that it can be cognitively difficult interacting across disciplinary boundaries. The second is based on this kind of landscape models, which you see in studies of cognitive diversity, but readapted slightly. This is a very abstract way of understanding things, and I'm with some colleagues in Helsinki pursuing it further, so actually doing some modeling, but this is kind of back of the envelope, just accept it as kind of back of the envelope way of looking at things. The basic argument here is that this kind of problem structured funding is really not a good cognitive framework for solving interdisciplinary problems, given the nature of the problem solving landscape. that interdisciplinary researchers might be confronted with, or often confronted with, if they engage in these projects. So here's the idea. Let's roughly model scientific problem solving as a search over a landscape of possible methods, approaches. This happens within disciplines, often over long timescales, of course, but for the standard project, we have 3 to 6 years. So when we often talk about this kind of epistemic landscapes, the peaks represent the kinds of optimal methodological choices. And in normal science, normal research science, we move around on these landscapes, we climb up hills towards the kind of optimal methodological choices through various heuristics that we might have for moving about that landscape. Okay, so imagine a problem which cannot be solved well by any one discipline, so it's not decomposable. Simply relying on one's traditional methods would lead to a suboptimal outcome. In theory, then this requires some kind of combination of existing methods which have to be integrated. So the task is to find that optimal set of integral methods and then do the integration. And so for sake of clarity, if we discretize discipline as n possible relevant methods, discipline M has m possible relevant methods, then I think, it's very kind of low-hanging fruit, but you can see that we have a kind of complexity issue at the outset. M and n methods respectively. So instead of having to just work through a space of m and n methods, you now have to decide between m times m methods. And so in that respect, there's going to be a much lower likelihood in general of discovering an optimal combination within this kind of time frame, or even of starting near an optimal combination, right? Depending on how difficult that landscape is. Further, we have to find combinations that are in fact capable of integration within a time frame. So the set of integral combinations are likely only to be subsets in that landscape. And there are probably always going to be good enough suboptimal solutions based on just the disciplinary decomposition. So that kind of frames the kind of choice scientists have in this environment, either confront that landscape or settle on the kind of suboptimal way of operating. That gives some sense, perhaps, of understanding why scientists make the choice they make, which is often to pursue the kind of multidisciplinary option. Yeah, we could spend a lot of time trying to find this kind of optimal or move towards this optimal. But if we can't even be sure that we're starting near an optimal with what we're doing without a lot of effort, then, well, we can get a good enough solution by just doing our own thing. So let's stick to that. Okay. And lastly, I'm going to bring Humphrey's account to bear, kind of model template analysis to bear. Not because I mean, Humphrey's notion of model template is a bit of a lower level than what I'm talking about here, but I think it's aspects of it can help explain what's going on when we talk about this crystallization phenomena. So the idea that scientists coordinate their activities within disciplines around a limited number of modeling templates, and they do this because this manages cognitive resources, facilitates standardization, and ultimately facilitates kind of theoretical development, right, to improve these templates. But we can't do that arbitrarily, right? We have to settle on a subset, a limited number of these to work on in order to get that kind of advancement, and that's kind of consistent with standard scientific practice. So why would we not expect to see something like that too with respect to interdisciplinarity? Whereas you can find basic ways of operating with respect to one another, why not kind of standardize those and then categorize those and then work to develop those? And in the model coupling aspect, you do see that kind of thing, right? Because then you see researchers worrying about, okay, if we're going to engage in this, can we start to find markup languages in which to all put our models so that we can begin to standardize this process, right? Or can we start to work theoretically on problems of calibrating these kind of large legacy models, which we stick together? Can we work on those kinds of mathematical problems to improve this process? And we find that environmental scientists start to work on those kinds of problems. And it's all in this kind of aim of, formalizing their kind of interactions, setting these interactions in a way that are manageable. But it's quite a step removed from this idea that, when we go into an interdisciplinary space, we're working on a specific problem and we're trying to come up with a novel way of handling that problem. Okay, What are the consequences for integration? So how should this kind of information, this kind of theoretical information shape our expectations? Well, integration, in the sense of coordinating and adapting our methods, is difficult due to cognitive as well as institutional obstacles. If there is integration, it's likely to be through modification to downstream elements in the system. That's an expectation we should have. So a bias towards more trivial, less transformative links. And researchers will often favor no modification if they can get a reasonably good answer out of no modification, particularly under time pressure, and will find ways to coordinate existing practices. And I guess model coupling is a very good example of just that, I would say, right? If you're engaging in model coupling, nobody needs to change their background practices to a significant degree, because you're just employing the kind of modeling practices you've been doing before. Okay. Some of these ideas might give some kind of support to the perceptions that ID research is kind of less rigorous or less deep research and sometimes suboptimal, right? So why might ID researchers have these perceptions? I mean, if we're being fair to them, maybe they just have basic biases towards one another. But if we're being fair to them, it's just the sense that you just don't get so far trying to do this research, and most likely you're going to take a suboptimal kind of outcome to get a result out of it. And you know, if people criticize the coupling process, it's often from that kind of perspective, saying, guys are just doing exactly what you've been doing before. You're not really getting to the heart of these problems. You're not really taking a transformative approach. So from our perspective, it just looks suboptimal with respect to the problem. Okay. So here's a kind of overarching then theory. I'm almost finished, by the way. So we have some resources for this, for building an overall theoretical understanding of methodological choices within these kinds of collaborative contexts. So the essential claims are something like this: that models of scientific practice that characterize disciplinary development over time are also relevant to those that characterize how disciplines engage in cross-disciplinary interactions. The collaborative ID research, to some extent at least, tends to recapitulate the cognitive, or tries to recapitulate the cognitive or methodological structure of disciplinary research through its concern, say, with templates, kind of relatively shallow modification and innovation, standardization, and I'm sorry, the window here is in my way, and innovation and so on. Okay, consequences. So what might be the kind of normative outcomes we might take from pursuing this further? If you believe me, what might we get out of this at a policy level, for instance? Well, firstly, I think we should take the cognitive structure of science seriously when planning ID and with respect to shaping our expectations of ID. And these may not be aligned with good models of scientific practice. We should treat ID collaboration more like disciplinary work and maybe stop exceptionalizing it, again, with respect to managing our expectations. What could this mean? Well, it might mean that we should be fair to the idea that approximating a problem as decomposable can provide an easier pathway to an approximate solution over insisting on an integrated one, which means not just favoring multidisciplinary work. There's a nice paper by Yuli Menes, you can find, in which she argues that. Getting it back into, say, the funding instruments, right? So not always prioritizing this thinking on integration. We should invest in theoretical work, which supports the development of interactions between fields and disciplines. So just not always this kind of problem-solving orientation or environment. And we should invest in longer-term relationships. It's clear that there's a lot of payoff in having people working together over continuing time, rather than just bringing people again to work on yet another specific problem and then going away again. And to get away somewhat more from the funding structure, or even funding in individuals, and I'll talk about that in a second. We should reconsider whether collaboration is always the best vehicle for interdisciplinary innovation. If that's really your goal, if you're expecting innovation out of interdisciplinarity, then, I mean, one could argue that collaboration brings too many constraints, both cognitive and institutional, and arguably relying on it might even serve to kind of reinforce rather than eliminate disciplinary boundaries in ID contexts, is everybody feels in this kind of problem-solving context, this funding context, that they have to go back to their disciplines to get stuff done. They're not really in a position to actually explore. And so if you look historically, interdisciplinarity has not always been collaborative. In fact, if you think about major innovations, major successes that have come through non-collaborative types of that have come through non-collaborative types of interdisciplinary engagement, there's quite a few. So we're talking here about researchers crossing into new fields, researchers for one domain entering a new domain. There's a nice book by Harman and Dietrich on outsider scientists. I encourage you to look at that, about scientists that have crossed into novel domains in biology, in this case, and made an impact on biology, people like Roland Fisher, for instance. Researchers trained in more than one field, combining them simultaneously. So I have a study of that, of researchers trained in both biology and biological experimentation and mathematical modeling, and the leverage they're able to get from the fact that they have deep level understanding of how both operate, and the kind of speed at which they can make cognitive decisions with respect to kind of getting the best leverage out of both of those, for both directing their experiment in a maximally informative way and also getting the best out of the experiment for their models. And that's a cognitive argument, right? That's an argument that there is really kind of cognitive capacity that comes out of being able to do. It's a kind of it's quite an individualistic perspective, but still, I think there is something there to being able to do both simultaneously. All researchers, of course, bring material from another field into their own. Evolutionary economics is a good example of that. None of these involve collaboration, right? Nobody's talking necessarily with anybody else outside their domain. Of course, when a researcher crosses into new fields, well, they do that, but they will collaborate. But I suppose even there, they don't necessarily need to. Okay. And it's also bearing in mind that there are some affordances of interdisciplinarity, which don't necessarily require collaboration to achieve. So you might be talking about the fact that from interdisciplinarity, it provides kind of methodological diversity on given topics, which improves the range of approaches considered, right? Gives you more to choose from when it comes to thinking about what might be the best approach, recognizing when there might be faults with particular methodological approaches. It can directly improve robustness if different approaches can converge on the same result, coming from different disciplinary backgrounds. And of course, engaging in it, if say you're moving into it, you're examining another field, can actually help develop your own understanding of your own field, kind of metacognitive perspective. And if you have this kind of systems view, then that's probably important for understanding where those modifications within your own field might come from. Okay, that's all I have to say. Thanks for listening. I hope it wasn't too long.